Hi all, this is the first of two videos that I'd like you to watch this weekend. This is your second shortcut rule for our calculus course, and it is the shortcut for the exponential function. And here it is. The derivative, again this is notation recall for derivative of a to the x, where a is a constant, it's a number like 2 or 3 or pi or e, any constant. Okay, the derivative of a to the x is a to the x times the natural log of a. Now, you might think, well, that looks awfully similar. The derivative of a to the x has a to the x in it. Well, times a times some constant, because remember the natural log of a is going to be a constant in this case. And a would have to be positive because we can only take the natural log of a number greater than 0. Okay? So it looks very similar. Well, let's take a look at the graph for just a moment. Here I have graphed y is equal to e to the x. And so if we were to graph this derivative, remember the graph of the derivative at a variety of points is the slopes of the curve. And so if you think about it, you all have gotten pretty good at graphing derivatives. If you think about it, the derivative is going to look very similar. In fact, the derivative for e to the x, I've mentioned before, is actually e to the x. It's the exact same graph. But if this had been, instead of e to the x, if it had been 2 to the x, for example, well, if y is equal to 2 to the x, then y prime, based on our new shortcut rule, is 2 to the x times the natural log of 2, which again is the original function multiplied by the constant, in this case the natural log of 2, and so its derivative would take on a very similar shape. Here's the graph, a sketch of 2 to the x, okay? And its derivative, 2 to the x times the natural log of 2, would look very, very similar. What if a were a number less than 1, but greater than 0, so 1/2? Well, you learned in a prior course, probably in your pre-calculus course, that this is an exponential decay curve. In this case, if this a value is between 0 and 1, then we know that our graph is going to decay towards 0, like what we have here. Okay? And so I want you to think for just a moment about what the graph of that derivative would look like. You might pause the video for just a second. Okay, so the derivative here is quite negative, so we have to mirror that in our graph. A little bit less negative, a little less negative, a little less negative, and that pattern continues, and so our graph is going to have a long-run behavior. It'll approach 0. Our graph's going to look something like this. Well, let's think about what the derivative of 1/2 to the x is, based on our shortcut rule over here, and why the graph is a reflection over the x-axis, or it's not an exact reflection, I apologize. It would not be an exact reflection, but it would be a near mirror image over the x-axis of our original function. Well, if y is 1/2 to the x, then y prime is 1/2 to the x times the natural log of 1/2. And the natural log of 1/2 is a number that is less than 0. If you think about what the graph of natural log of x looks like, okay, this is the natural log of x here. We know that this value is 1, and it has a vertical asymptote of the y-axis. And so the natural log of 1/2, if you think about the output, the y value at 1/2, natural log of 1/2 is a number which is negative. In other words, this constant is negative, and this negative number multiplied by the curve 1/2 to the x is going to be a reflection and then a stretch or compression of 1/2 to the x, which is what gives us this sketch. All right, so let's do, there's some, what I was trying to give you there was some graphical things to think about as to why the derivative of a to the x is a to the x times the natural log of a. Let's go ahead and just work through a number of examples now using this new shortcut rule. So here we've got the sum of two functions. Well, we know the derivative of the sum of two functions is going to be the derivative of the first, in this case, plus the derivative of the second. So we'll derive each separately. If y is 3 to the x, then y prime would be 3 to the x times the natural log of 3 plus whatever the derivative of e to the x is. Well, the derivative of e to the x is e to the x times the natural log of e. But keep in mind again that the natural log of e is 1, And so we just write plus e to the x. In other words, y prime would be 3 to the x times the natural log of 3 plus e to the x. So again, the derivative of e to the x is a special one. The derivative of e to the x is e to the x. If your base is not e, say it's 2, or 5, or 3, then your derivative is a to the x times the natural log of a, and we'd have to write the natural log of whatever that constant is. All right, let's take a look at this next example. So y is equal to 5 to the x plus 3x squared minus 2 over x. Of course, you're in the habit now of manipulating 2 over x as 2x to the negative first. So now I've got my k times x to the n form, which was our first shortcut rule. Again, we'll just derive one piece at a time. So y prime would be 5 to the x, ln 5, plus 6x to the first, and then it would be plus, in this case, 2x to the negative second. It's plus because there's a negative 1, and this again was a negative out in front, so negative times a negative makes this a positive, 2x to the negative second. You're fine to leave negative exponents in your derivative, but keep in mind you could also write this as 2 over x to the positive second. So there's your derivative. Next, y is equal to e to the x minus e, and so y prime is the derivative of each individual piece. Well, the derivative of e to the x is e to the x. The derivative of negative e is 0. Remember, negative e is a constant, and so if we derive a constant, we get a slope of 0. So y prime is just e to the x. Next one, y is equal to 2 times 3 to the x plus 5 times e to the x. So y prime then would be, now think about this with me, this is k, all right? If you have a constant and you're multiplying by some function, f of x, I'm calling 3 to the x a function, then the derivative is just going to be k times the derivative of f of x. Very similar to what we've worked on with the first shortcut rule. So 2 times 3 to the x has a derivative of 2 times 3 to the x times ln 3. Now, this right here is the derivative of 3 to the x. 2 is just our constant rewritten. I want to give you an alternate example to think about. Sidebar here. If y had been 5x squared, recall what we've done is we've derived x squared and then we've multiplied it by the constant. And so y prime was 5 times 2x, or 10x. Well, we're doing the exact, not 10 to the x, I apologize, 10x. I wrote it again. 10x, there we go. So in this case, we're doing the same thing. We have a function 3 to the x. That function is being multiplied by some constant k, in this case 2. And so our derivative is k, 2, times the derivative 3 to the x ln 3. Of course, we need to add to that the derivative of the second piece. And the derivative of 5e to the x is 5 times whatever the derivative of e to the x is. So here's k, here's our function. Well, the derivative is 5, in this case k, times the derivative of e to the x, which we know is e to the x. And so here's your derivative function. All right. So let's jump to the next page. I am going to encourage you to pause and to try these on your own. Take 5 or 10 minutes, maybe a few more. Try them on your own, and then I'd like you to watch the video and take a look at the work solutions. I'll give you a heads up. I would say that this problem is pretty challenging. This piece in particular may not be obvious what to do. This one is going to be pretty challenging. So is this one, and that's largely because the exponents are written differently than what you've seen so far. So think in that one. So think maybe about those 4, but try all of them. I'm telling you right now, those 4 will be challenging. So maybe pause the video, give them a try. Okay, let's start with f of x. Well, if f of x is 2e to the x plus x squared, then f prime of x is the derivative. So here's k, here's the function that needs to get derived. So we've got the derivative of 2e to the x is 2e to the x, plus, of course, the derivative of x squared is 2x to the first. There's f prime. I'll jump down to g prime. and I hope it's apparent that we need to rewrite this as pi x to the negative 1/2. So remember, pi over the square root of x is the same as pi over x to the 1/2, and if we jump the line and change the sign, now you're ready to derive this piece. It's in the format k times x to the n. So g prime of x then is 12e to the x plus 11 to the x times the natural log of 11. And in this case, let's see, it's going to be a plus 1/2 pi x to the negative 3/2. That pi right there is this pi. It's plus because a negative 1 times a negative 1/2 gives us a positive 1/2. And then when we subtract 1 from our exponent of negative 1/2, we get negative 3/2. H of x. H of x is 4 times 10 to the x. Again, I want you to keep in mind that's a constant. That's k. That's what we're deriving. Okay? And then we've got to derive this as well. So h prime of x is the constant rewritten times whatever the derivative of 10 to the x is, which is 10 to the x times the natural log of 10. Okay? And then we have to subtract 3x squared. The derivative of x cubed, of negative x cubed, is negative 3x squared. All right? Let's look at I of t. I of t, I wrote this very much on purpose because I wanted you to see the fact that here we have a to the x. It was written in a pair of parentheses. Okay, so that's a to the x. And then here you have a, but a is actually, I'm going to rewrite this piece, this whole piece. This is the same as saying take away 1/4 times 3 to the x. Make sure you're good on that idea. A, in this case, is negative 1/4. Or I'm sorry, k. I apologize. K, in this case, is negative 1/4. And then there's your a to the x. So when we go to derive, I prime of t would be 3 over 4 to the x times the natural log of 3/4. Again, keep in mind the natural log of 3/4 is going to be a negative number because we've taken the natural log of a value less than 1. And then we have to derive this piece, the second piece, which I've rewritten as negative 1 over 4 times 3 to the x. So we've got negative 1 over 4, there's your constant, times 3 to the x, ln 3. Okay. All right, let's take a look at this this other side. So these are the 4 that I mentioned were somewhat challenging. You really have to you got to know your exponent rules here. And there are a lot to remember, but the more you work with these, the better you'll get. So I'm going to rewrite j of x first. This is not j prime yet. J of x, if we have 3 to the negative x, that's the same as 1 over 3 to the positive x. And so that looks a lot like this over here. We're doing essentially the same thing. So 3 to the negative x, and the reason I'm saying that, maybe I should break it down one step further. The reason I'm saying this is 3 to the negative x is because this is the same as 3 to the negative 1 to the x. Okay? Power to a power you can multiply, so I'm saying 3 to the negative 1 to the x. Well, 3 to the negative 1 is 1/3, or 1 over 3 to the first. And then we've got plus 2 times x to the 1/3. And now we are ready to derive. So let me change colors. J prime of x then would be 1 over 3 to the x times the natural log of 1 over 3. And then we've got plus 2 over 3 x to the negative 2/3. There's your old, so this piece was your first shortcut rule that you learned last week. And this piece is your second shortcut rule, exponentials. K of x, again, you're going to want to rewrite here. If k of x is e to the 1 plus x, that's the same as e to the 1 times e to the x. So there's going to be a lot of manipulation that needs to continue in these next couple of lessons, these shortcut rule lessons as well. And that's what Chapter 3 is all about, shortcut rules. So again, think about it. E to the 1 times e to the x is e to the 1 plus x. You've got two numbers of the same base, okay? if you're adding, or if you're multiplying two numbers of the same base, then you're adding your exponents. Okay? So, if you think about this, this is the same as e times e to the x. This is your constant out in front. Okay, that's your constant. That's the function that has to get derived, e to the x. We know what the derivative of e to the x is already, so let's derive it. K prime of x is going to be equal to e times e to the x. So again, this is the derivative, I'm saying. And if you think about it, your derivative, there's your constant e, so here it is, times whatever the derivative of e to the x is. Well, the derivative of e to the x is e to the x. And it just so happens that e times e to the x is, once again, e to the first times e to the x, which is e to the 1 plus x. In other words, the derivative of e to the 1 plus x is also e to the 1 plus x. Okay? L of x. I'd consider this to be a challenging problem because we have to manipulate first. So I'm going to rewrite L of x as, let's see, 3 to the x times 3 to the negative second. Now take a moment and think about that. Same base, you're multiplying. What do you do with your exponents? You add them together. There's your x plus negative 2, or x minus 2, same thing. So here is your function 3 to the x. I'm going to rewrite 3 to the negative 2 as 1 over 3 squared, or 1 over 9. So this is really 1 over 9 times 3 to the x. So that's still L of x we have not derived yet. I rewrote L of x as k times a function. And we know then that L prime of x is k, 1 over 9, times the derivative of the function. And the derivative of 3 to the x is 3 to the x times the natural log of 3. There is your derivative, L prime of x. Let's try one more. M of theta. Well, if m of theta is negative e to the x minus 2, again, I'm going to manipulate. I'm going to write this as negative e to the x times e to the negative 2, which we could call negative 1 over e squared times e to the x. All right. Again, negative 1 over e squared is a constant. E to the x is a function. And so we could say that m prime of, now this, I should have had this labeled x, or I should have had this labeled theta. One or the other should have matched, though. We'll just call it m of x. So m prime of x then is, well, there's my constant, negative 1 over e squared, times whatever the derivative of e to the x is. Well, the derivative of e to the x is e to the x. Okay? And so, once again, you'll see that we end up with negative e to the x minus 2. Give that some thought. The derivative of negative e to the x minus 2 is also negative e to the x minus 2. Okay, I've got one more slide in this video. And then again, I'd like you to watch one more video to get you through the weekend. But I have p of t is equal to the natural log of 3 to the t. Now watch your exponents here. What I'm saying is that's a for, in other words, a to the t. How do we derive a to the t? We get a to the t times the natural log of a. So it's going to get a little silly looking here. But if p of t is natural log of 3 to the t, then p prime of t is the, let's think about this for a second, it's going to be the natural log of a, so that's the natural log of the natural log of 3, which is still going to give us a number because the natural log of 3 is a number, a constant, greater than 0, then we can take the natural log of it. So I've got the natural log of a times a to the t. Natural log of 3 to the t. Okay? Again, the derivative of a to the t is a to the t ln a. Okay? And so this is the same as, maybe you're thinking of it as natural log of 3 to the t times the natural log of the natural log of 3. Of course, those are the same. Order does not matter. We're multiplying, and so there's your derivative. Okay? Just for kicks, to make it one step more complicated, let's think about this. R of t is equal to, there's my constant, there's my function. Okay, so I've got the natural log of 5 times 5 to the t. R prime of t then is my constant, the natural log of 5, times a to the t times ln a. And so here you actually have the natural log of 5 times the natural log of 5, which is the natural log of 5. Another way to think about it is this is the natural log of 5 squared. Take the natural log of 5 and multiply it by itself. You get the natural log of 5 squared times, in this case, 5 to the t. All right, let's look at a word problem. I want you to see this in real-world context. So the population of Connecticut is modeled by P of t is equal to 3.59 times 1.02 to the t, where t is years since 2013, and we'll call this million people in Connecticut. So 3.59 million was the initial value in 2013, and the population of Connecticut is growing because this 1.02 is greater than 0. That tells us we've got exponential growth, and we'd say it's growing at 2% per year. That's its annual growth rate. So number one, is Connecticut's population growing or decaying? It's growing. If this number had been between 0 and 1, then we would have called it decay, but it's greater than 1, so it's growth. Find and interpret P of 0. Let's start there. Well, P of 0 is if I were to put 0 in for t, I get 1.02 to the 0, which is 1, and 3.59 times 1 is 3.59. Let's interpret it. P of 0 equals 3.59 means that in 2013, Connecticut's population was 3.59 million. I'll come back to the derivative in just a second, but let's interpret P of 2 then. So P of 2 is 3.59 times 1.02 to the second. I'll take a moment and punch that in. I have my calculator by me. And I'm getting 3.735 approximately. 3.735. And if I'm interpreting that, I'm saying that in the year 2015, because this is 2 years since 2013, Connecticut's population is estimated to be was 3.735 million people. Now, for the derivative, remember a derivative is a rate of change. It's change in dependent divided by change in independent. So this is going to be people per year. Okay? So P prime of 0. Well, in order to get P prime of 0, I need to find P prime. So P prime of t is 3.59 times 1.02 to the t times the natural log, ln, of 1.02. There's my derivative model. Okay? That's the function that we'll use to model the derivative. Now, what is P prime of 0? Well, if I want P prime of 0, then I'm going to put 0 in for t. And I get 3.59 times 1, because 1.02 to the t is 1, times the natural log of 1.02. So 3.59 times the natural log of 1.02, I am getting approximately 0.071. So P prime of 0 is about 0.071. Now, this again is, I said people per year. I should have said millions of people per year. Okay? And so 0.071 million, 0.071 times 1 million is 71,000 approximately. And you can be even more accurate, but I'd say about 71,091, double check me by using your own calculator, people per year. And we know that this is growth, so it's growing at 71,091 people per year in 2013. That was its rate of change. Okay, we know it's growing because it's positive. If it had been negative, if the first derivative had been negative, then it would have been not increasing but decreasing. Okay? And so again, we'd say in the year 2013, Connecticut's population was growing at 71,000 people per year, approximately. All right, P prime of 2. Well, I go back up to my derivative, and I substitute 2 in this case. So before, we said this was 1, but it's not 1 anymore because t is not 0 anymore. I'm going to go ahead and I'll say, all right, we're going to put 2 in. We'll put 2 in for t. And so 3.59 times 1.02 to the second times the natural log of 1.02 is approximately 0.0774 if I'm rounding to 3 places. Again, it's positive, and so in context, we are saying Connecticut's population is growing at, or was growing at, approximately 74,000 people per year in the year 2015. So, in other words, in 2015, we would expect this, Connecticut's population to grow by another 74,000 people. Okay, that's all I have for this first video. Please watch the next one. It will be shorter. I'm going to introduce your next shortcut rule out of section 3.3 called the product rule.